So here we have uniform distribution. What is so special about probability distribution is the area under the curve should equal to 1. So that would be the total area of this rectangle. It should be 1. But we also know that the area of the rectangle is the length at the bottom times the height. And what is the length at the bottom? Well, we could count as 1, 2. But in general, how do we come up with a formula for the length? It will be the upper bound minus the lower bound. So we will have 2 minus 0, which should equal to 2. Now 2 times what equals 1? All you have to do is to take the reciprocal, and 2 times 1 over 2 equals 1. So I'm just going to go ahead and spell out 2 minus 0. So that gives us 1. And it helps us to find the height of this rectangle, which is 1/2. Now let's look at another example. So I have a second rectangle. And once again, I know that, let me use a different color. I know that the area should be 1. And it equals the length at the bottom times the height. What is the length at the bottom in this case? Notice I changed the boundary to go from 1 to 6. So in this case, the length at the bottom is 6 minus 1. And 6 minus 1 equals 5. Let me do a little calculation over here. And 5 times what equals 1? All you have to do, once again, is to take the reciprocal. So that will be, well, let me spell it out. 6 minus 1. So 5 times 1 over 5 equals 1. So in this case, the height of the rectangle is 1 over 5. Okay, so now we know this. Let's calculate some probability. The first one, I would like to calculate the probability when x is between 1.5 and 3.5. Now, what is so special about the, the uniform distribution and normal distribution is with or without equal sign, the probability remains the same. So the difference is really whether I have a dashed line or solid line around the boundary, but the area does not change. Now, to find this probability, all we have to do is to find the area of the shaded region. And to find the area of that shaded region, we need to know the length, oops, the length at the bottom, so that would be this, and the height. How do I find the height? The height, according to what we learned above, notice this one is 1/2 and this one is 1 over 5. How do I get those numbers? I will use the upper bound of that larger rectangle minus the lower bound of that larger triangle, and then take the reciprocal. So 4 minus 1, and take the reciprocal. That will give us the height of this rectangle. Now the length at the bottom equals 3.5 minus 1.5. So the upper bound minus the lower bound for the shaded region times the height, which is 1 over 4 minus 1. And a little shortcut is, from now on, all you have to do is take the upper bound, take the difference between the upper bound and lower bound of that shaded region and divide it by the upper bound and lower bound of the entire rectangle. And before I put the information into my graphing calculator, I want to put a set of parentheses around the top and the bottom. So just to make sure that the order of operation is correct. So this is why I would do parentheses 3.5 minus 1.5. Close the parentheses and divide it by parentheses 4 minus 1. Close the parentheses, and that is my answer. Now, depend on the instruction, you might have to round it to certain digits, or you might have to convert that to a reduced fraction. So just pay attention to the instruction. In this case, I have 2 over 3. Now let's look at another example. So in this case, I'm looking for the probability of x greater than 4. Now, to find the probability, what I have to do is I need to find a fraction. That's what I did over here. And upstairs, I have the difference between the upper bound of the shaded rectangle and the lower bound of that shaded rectangle. So I have 5 minus 4. And downstairs, I will have the upper bound of that larger rectangle. So once again, it's 5. And the lower bound of that larger rectangle. So that would be 2. So my answer will be 1 over 3. Next example, we want to find the probability of x less than 3.1. Now in this case, we have to shade the appropriate area all by ourselves. Let's look at the inequality. Notice the inequality point to the left. So we will shade the left-hand side. Now once we know that, all we have to do is to subtract the lower bound from the upper bound within that shaded rectangle. And downstairs, I have the difference between the upper bound and lower bound of that larger rectangle. And you could punch the answer, well, this expression into your graphing calculator. Don't forget the parentheses. And you should have your answer. Now, the next example, we are dealing with probability of x less than 0.8 or, so one or the other, x greater than 3.4. So we're looking at a split region. Now, we could calculate the area of this rectangle, of those two shaded rectangles separately. And that would be an acceptable answer. Or alternatively, we could also say that, let me see what color I want to use. We could say that, hey, I could just calculate the area of this purple region and use the fact that the area of this entire rectangle is 1. So I just subtract the area of this purple region from 1. So that purple region is x goes from 0.8 to 3.4. And once again, with or without equality, it's it's fine. So let me have it just for fun. Let me have an equality here and drop that equality on the other side. It makes absolutely no difference for continuous random variable or for uniform and normal distribution. So for here, all we have to do is subtract this fraction from 1 upstairs, upper bound minus lower bound for the shaded region, and downstairs, upper bound minus lower bound for the larger rectangle. And punch that into your graphing calculator, you will have the answer. Okay, so now I have covered just about every different type of inequality we could imagine. Now, the very last one, I would like to cover a very, very tricky case. That is to find the probability of x strictly equal to 1.1. Now, for binomial distribution, it's possible to calculate the probability of x exactly equal to a particular number. And that probability is not necessarily zero. But for continuous random variable that would be uniform and normal, this probability is always, always zero. Regardless what number I'm putting in over here, I could have a 1.5 or 2, whatever number you could imagine. As long as we have equal sign, this probability is always zero. One way to verify that, let's don't verify that if you trust me. That is the special case for uniform distribution as well as normal distribution. If you have an equal sign, this probability is always, always zero. And if you wish, I would be happy to go through the proof, the mathematical proof with you, but I won't confuse you with this introductory video. Okay, let me know if you have any questions.